Hi folks, here is the video for 2.4. I apologize for the technical difficulties earlier and I appreciate your patience. And so let's do a quick review of what we talked about at the very beginning of class. So as always, we started with our what we know. And in particular, we're talking about what do solutions look like? And that was something that I posted a short video on for section 2.1. So if you haven't taken a look at that yet, please take a look at that before homework number 1. I think you'll find it helpful. What else do we know? Well, we've also talked over the last few days about all the important things we need to remember from Calc 2. So a lot of integration techniques, and in particular, we probably want to add U sub here to our list of basic integration formulas. But knowing that we'll be using integration by parts and integration using partial fractions, it would be important to brush up on those skills, okay? Additionally, we took a look at identifying and solving separable differential equations on Tuesday. And then on Wednesday, we took a look at solving linear differential equations. And so today, we're going to learn about one more type of equation and how to solve that. And that'll really round out the fundamental skills we need from first order differential equations, okay? So algebraically, we're going to solve something called exact differential equations. All right, so knowing that that's what we know, and this is what's going to be new, let's start talking about the concept here. Okay, now as I mentioned yesterday, when we're talking about these types of differential equations, I generally like to start with a very variable heavy equation, something that's super general so that we can then list out the steps and use that to guide our work in all sorts of exact differential equations. And today we're actually going to take a look at an actual differential equation and use that because in this case, it'll be easier if we see an actual differential equation before we look at the generalization piece, okay? So let's consider the differential equation that we have right here. 2xy minus 9x squared dx plus 2y plus x squared plus 1 dy. And one thing that you'll notice that we have here is that we are looking at a first order equation, right? And we want to start by imagining. So yesterday we imagined a magical function that we called mu. And today, let's imagine that we have a function called phi of xy. And for this particular equation, let's say that phi of xy happens to be y squared plus x squared plus 1y minus 3x cubed, okay? Now, obviously, I've chosen this purposefully so that we'll be able to solve the differential equation, but this is going to be a really important skill for us is to think about how do we have this phi function, okay? So let's imagine we have this phi function. And as a quick review, let's talk about partial derivatives, okay? And so one way that you might have seen partial derivatives written in the past is partial phi, partial x. And that would indicate that you're going to take the phi function and take a partial derivative with respect to x. So that little x there means the same thing as partial phi, partial x. And so if we approach this phi function, pretending that y's are all constants and x's are the only variables, let's take a derivative. So if y squared is a constant, that means that derivative is 0. Plus, we're going to have a constant multiple over here. So we'll actually get 2x, which is the derivative of x squared, times y, which is a constant. And then we'll take the derivative of negative 3x cubed and get negative 9x squared. Okay. Let's also use the same phi function and find d phi dy. In other words, the partial derivative with respect to y. So d phi, partial y. We could also write this as phi sub y. And if we go back to our phi function, now we're going to treat x as a constant and y as a variable. So the derivative of y squared is 2y plus, we'll have a constant multiple here, x squared plus 1 is the constant times 1, because the derivative of y is 1. And then finally, negative 3x squared, if I take a derivative with respect to y, is going to be minus 0. Okay. So let's go ahead and clean these up for a moment. I wrote some extra numbers we don't need, like the zeros and the ones. Okay, let's see what we get. We get partial phi partial x equals 2xy minus 9x squared. And we get partial phi partial y as 2y plus x squared plus 1. Now, if you look back at the original differential equation, some of this should actually look very familiar. Our phi of x is 2xy minus 9x squared. And wow, look at this, 2xy minus 9x squared. Huh. Okay, let's try taking a look at phi sub y, or the partial derivative of phi with respect to y. We got 2y squared, or 2y plus x squared plus 1. And wow, over here we have 2y plus x squared plus 1. Well, it turns out that that is not a coincidence. All right, it is not a coincidence. In fact, this function that I said I want you to imagine was chosen very carefully so that this would happen. Okay. Now I'm going to do a little substitution here. In this differential equation, everywhere I see 2xy minus 9x squared, I'm going to write phi sub x. And everywhere I see 2y plus x squared plus 1, I'm going to write phi sub y. Okay. So sub into the differential equation, and we're going to get phi sub x dx plus phi sub y dy equals 0. And again, this is the same as the other light purple, and this is the same as the other yellow. Okay. Now it turns out that this left-hand side can be written as the derivative of a product. Okay, so it's very similar to that linear equations we saw yesterday. In fact, we can write this left-hand side as d dx of the function phi, comma, of xy. Okay. Now, once we have that derivative of a function, how do we get rid of the derivative? Well, we're just going to integrate, just like we did with the linear. And so if we integrate the derivative of phi of xy, we have to integrate the other side as well. Okay. And now when we integrate, we end up with phi of xy equals a constant. Now, this is actually going to give us our solution, okay? So this phi of xy equals c is going to be able to give us our function that we imagined in the first place, okay? And so what we're going to do when we sort of solve these problems is we're going to actually start here, and we're going to be able to find the phi, and that phi will end up being our solution, okay? So before we move to an example, let me sort of write this out in general, okay? So in general, we are going to have some function. We will have the following. We're going to have some function with x and y times dx plus a different function of xy times dy equals 0. And if we sort of zoom back out for a moment, we'll notice that that matches the structure we have over here in our example. And in particular, m of xy is the yellow one, and n of xy is the purple one. Now, why mathematicians choose to use M and N when they can look so similar, really beyond me. But let's just be really clear with our handwriting as best we can, all right? That the first one, the one with the DX, is a capital M, M as in Muppets, and the one next to the DY is an N as in the only word I can think of right now is nuggets, which actually kind of rhymes with Muppets. So maybe that wasn't a good idea, but you get the idea. We have an M of XY and an N of XY. And what's going to be so special about this is we're going to let phi of XY be some function such that the partial phi with respect to x is actually going to equal m of xy, and the partial with respect to y of phi is going to equal n of xy, okay? So we're keeping in line with the purple and the yellow. This m is going to actually be the partial derivative of phi with respect to x. And this n is going to be the partial of phi with respect to y, okay? So then we have phi of x dx plus phi of y dy equals 0. And from here, we'll be able to pack it back up into the product rule, okay? And we'll get d dx of phi of xy equals 0. When we integrate both sides, we'll get phi of xy equals c, and this will be our solution. Okay. Now let me zoom out here for a moment in case you want to stop the video. You can see that page. All right. So all of that being said, let's go ahead and actually try some examples. Okay. So we have a few examples here for us today, and they're all going to model this idea of the exact equation. All right. Now we are, oops, totally wrote that in the wrong place. I'm going to go ahead and cut and paste this so that it is in the proper location right here. It's just not a great day with technology. Thanks for being so kind. All right, so let's get to our examples. So example 1, we have the question that we actually started with, right? We've seen this question. We kind of used it to set things up and explain where we get this phi function from, but we didn't actually solve it, okay? So now we're gonna take that information, we're actually gonna be able to solve it, all right? So here's how we're gonna frame these. Let's do our sort of bigger structure in the blue. The first thing you want to do when you look at an example is you want to say, is this an exact equation or not? And it turns out that for exact ones, we actually have a test. We can test to see whether it's exact or not. So here's the test. We're going to take our m of xy. Right? We know that equals 2xy minus 9x squared. And we know that this is also equal to phi sub x, phi sub x. And we're going to take the second one, n of xy, equals 2y plus x squared plus 1. And we know that that is phi sub y. Now, if you sort of go back into your brains to what we learned about partial derivatives, we might remember this, okay? So recall that partial x is not necessarily equal to partial y, okay? And in this case, we can see that those are not equal. However, for continuous functions, make sure we have enough room, phi of xy actually equals phi of yx. In other words, if you take the partial with respect to x and then again with respect to y, and you compare that to what you did if you took the partial with respect to y and then the partial with respect to x, you should get the same thing, okay? So here's how we're going to do this. We found our partial x and our partial y. So the partial x, I'm going to take a derivative of this with respect to y to get partial xy. That will give me this part, partial xy. And then I'm going to take my partial y and take a derivative with respect to x, and I'll get partial yx. And if these two are equal, then we have an exact equation, okay? So let's do our partials. We'll get partial xy equals, let's see, 2x minus, y is the variable, so minus 0, or 2x. Well, what about partial yx? So this time x is the variable and y is the constant. So 0 plus 2x plus 0, which is 2x. Well, our partial, I'll have a better day with technology later. This partial xy is equal to 2x, and this partial yx is also equal to 2x. So it turns out that this differential equation is exact, okay? It's really important when we're considering whether something is exact or not for us to go ahead and test whether it is or not first, okay? So once you have tested and confirmed that it is indeed exact, then we can move on to the second step, okay? So we found that this is exact. And so what we're going to do next is we are going to find phi of xy. All right. Now, we actually have two ways potentially to find phi. And I'm going to show us both ways in some of the problems, okay? But I want to make sure that we are okay with knowing that we can choose one of the ways, and sometimes one of the ways will be better than the other way. Okay, so I'll try and be really explicit about that in the video. So we're going to find phi of xy using phi equals the integral of m dx. All right, so in other words, if m is the partial with respect to x, then we have to integrate it with respect to x to get back to where we started. And similarly, we could use phi equals the integral of n dy. And the reason why it's n dy is because n is the partial with respect to y. So to go back to phi, we have to take the integral with respect to y, okay? So for this first example, I'm gonna go ahead and do both ways, all right? So we'll do the integral of m dx, we'll also do the integral of n dy. But as we do future examples, then we'll be able to tell which way is gonna make it easier for us, okay? And we always wanna choose the most efficient way. So let's start by finding integral of m dx, all right? So phi equals the integral of 2xy minus 9x squared dx. And let's go ahead and integrate with respect to x. So we'll get x squared y, because remember y is like a constant, minus 3x cubed, because we're doing power rule for integrals. Now, at this point, you are probably very tempted to say, I'm going to put a plus c on the end. But we have to hold on a little bit, okay? Because our plus c here could only be something that involves y, right? Because we took a derivative with respect to x, so anything that had a y in it, that went away if it only had y. And so the way we write our plus c here is we say plus h of y. Like it had to come from some function that only involved y. All of those went to 0. Okay. Now, similarly, I could have said, I'm going to find the integral of n dy. And I could have set it up this way. Phi equals the integral of 2y plus x squared plus 1 dy. And when I integrate with respect to y, I'm going to get y squared plus x squared y plus y plus, now we don't want a plus c, because remember, we're doing sort of a partial situation. And we don't want an h of y, because that would have given us some sort of derivative. We have to change this to h of x, okay? Because any function involving only x, when we take a partial with respect to y, will actually give you 0, okay? All right, so once we find our phi, then we need to find h of y or h of x, depending on which way we solved it. And so our step 3 is going to be precisely that. We are going to find h of y or h of x, depending on which method we used. And again, I'm going to show you both this time. Okay, so if you used phi equals the integral of m dx, then use phi sub y equals n to find h of y. Okay, so if you use the one on the left with m dx, then we're going to use phi of y equals n to find this h of y function. And here's what I mean by that. We're literally going to take phi of y and set it equal to n. So we're going to go back to our phi. We're going to take a partial with respect to y. So that's going to give us x squared minus, what is the derivative? Oops, what is the derivative of negative 3x cubed with respect to y? It's 0. And what is the derivative of h of y with respect to y? Plus h prime of y. So our phi of y is our partial of what we found above with respect to y. And we're going to set that equal to whatever n was in our original equation. And our n was 2y plus x squared plus 1. Okay, so this was our n in the equation. Now we have a little equation, and we're going to be able to isolate h prime of y. Okay, so notice that we can go ahead and subtract x squared from both sides, and we end up with h prime of y equals 2y plus 1. Well, we don't want h prime of y, we want h of y. Turns out we can go ahead and integrate now. So we'll get h of y equals y squared plus y. So let's make a note here that we integrate. And we're going to go ahead and put a plus c on the end, all right? Knowing that this c is going to get collected with another c later on, all right? So let me zoom in for a little bit, or zoom out rather, and let's just kind of make sure we're okay with where we are. So we said, first of all, we should start with, is it exact or not? And we talked about how we could tell. Once we've confirmed that it is exact, we have to choose one of two setups. And for this first example, I'm doing two different setups so we can see that they both work. But in the future, we really only want to choose one and go with that one. And in fact, we want to choose the easier one and go with that one. So far we have integrated m with respect to x and gotten a possible phi function. But in order to finish, we need to find h of y. And so that's why this next part is helpful, because it helps us find h of y. Now, the other way, we did our setup where we integrated n with respect to y. And instead of ending up with an h of y, we ended up with an h of x. And so in this step 3, we're going to need to find h of x. So let's write a similar sentence here. If you used phi equal the integral of n dy, then use phi sub x equals m to find h of, right? So you can see that we're sort of switching this up. We're looking for phi of x now, and we're setting that equal to m. Now, how are we going to find phi of x? We're going to take our phi and we're going to take a derivative with respect to x. And so that turns out to be 0 plus 2xy plus 0 plus h prime of x. And that is our phi of x, or phi sub x. And then our m, we're going to grab the m from the original equation, and that should give us 2xy minus 9x squared as our original m. Okay. And it's good if things start to cancel out, right? We sort of created it to be that way. So this 2xy and this 2xy are going to go away. And we have h prime of x equals negative 9x squared. Now, just like over here, where we had h prime of y and we had to integrate, now we have h prime of x, and to get h of x, we're going to need to integrate. And so we'll get h of x equals, let's see, negative 3x squared plus c. All right. All right. We've got one last step, and that is we are going to replace h of y or h of x in our phi of xy from step 2. Okay, so we're going to go back to step 2. We're going to copy down our phi. So on this side, we have this as our phi. And on this side, we have a different phi. But everywhere I see an h of y, I'm going to plug in y squared plus y plus c. And everywhere I see an h of x, I'm going to plug in negative 3x squared plus c. Okay. So let's go ahead and substitute. We've got phi equals x squared y minus 3x cubed. And now here comes the h of y part, plus y squared plus y plus c. And remember, based off of what we said in general, all of this has to equal some constant, okay? Now, some people like to do this intermediate c as like a k, just so they know that it's different from this C. You could do the same thing if you call this like C1, you call this one C2, that would be okay, all right? Now, let's go ahead, and the last thing we're gonna do is we're just gonna take this C and combine it with the other C. And so we'll get x squared y minus 3x cubed plus y squared plus y equals C. And I'm going to do one more thing, not because I have to, but because I want to show you this is actually the same thing that I said at the very beginning when I was like, let's imagine this, okay? So I'm going to bring this y squared to the front. And then I'm going to go ahead and grab x squared y, and I'm going to factor out the y. So x squared plus 1y. And then I'm going to put this x term at the very end. Right. Now I'm going to pause right now for you to scroll back up to the beginning. And hopefully you'll notice that this is exactly what I was like, let's imagine we have some function, okay? So all of this problem was to show us how did we come up with that function. Now, if we chose the other setup, we should still get the same answer. All right, so we're gonna grab our phi from this side. We're gonna plug in our h of x at the end, and let's see what happens. And we'll end up with phi equals y squared plus x squared y plus y minus 3x squared plus, let's call this C1, equals C2. And we want to go ahead and move the c's to the same side. So y squared plus x squared y plus y minus 3x. Oh, this is a cubed, sorry. 3x cubed equals c. And I can tell right here in these middle two, if I factor out y, I get y squared plus x squared plus 1y minus 3x cubed equals c. And so we've shown in a very long problem, because we actually did 2 problems in one, all right? So here it is all on one screen. We showed that we could first start by determining, is it exact or not? And if it is exact, we go ahead and proceed with the next 3 steps. When you do a problem, you only need to choose one of these sides. So either you choose the steps on the left or you choose the steps on the right. Completely up to you, okay? As we work through the other examples, we'll start to see that some choices will be easier for us than others, okay? Sometimes it won't matter, like this one, and sometimes one will be easier than the other. So it's worth kind of setting up both ways to see which one might be easier, okay? So I'm going to go ahead and do this video in 2 parts. So I'm going to pause right here, and then I'm going to come back and finish the rest of the example, okay? So see you folks back here in a little bit.